question 1 is really just a bit of recap on some ideas from the first term but applied to alcohols and specifically to ethanol. So first, it's just a reminder about these different types of formula that you need to be able to generate. So first of all, it wants a displayed formula for ethanol. So eth means 2 carbons, ol means that you have OH, so an oxygen and then a hydrogen like that, and it's ethan, so there's only a single bond between the carbons, and if you count them up to make sure each carbon has 4 bonds, that gives you that as the displayed formula. The thing to watch out for there, the common mistake, is because you're so used to writing about OH groups to forget that obviously there's a bond there between the oxygen and the hydrogen. So if it asks for a displayed formula, you have to show that bond explicitly. Structural formula means you shrink that down all onto one line. So you get CH3 for the first carbon, CH2 for the second carbon, and then OH stuck on the end. A skeletal formula, you've got 2 carbons, so there's the first one, there's the second one, and then you just put OH down in the normal way. You only abbreviate carbons and hydrogens. Carbons as points at the end of the line, hydrogens omitted altogether, but of course, as you know, you can figure out how many hydrogens there are by realising that the carbon must have 4 bonds altogether. So that's the skeletal formula. And the molecular formula, you just list how many carbons, which is 2, how many hydrogens, which is 3 plus 2 plus 1 is 6, and then how many oxygens, so C2H6O. You quite often see this written down as the formula for ethanol, which is a perfectly valid formula, but it isn't any of these. In particular, it's not acceptable as a structural formula. You've got to lump all the hydrogens together. So that's the molecular formula. Okay, so now it invites us to put partial charges on the molecule. This is about recognising that the dominant feature in alcohol chemistry is that this oxygen is more electronegative than either the hydrogen or the carbon that it's bonded to, and that gives it interesting physical properties, unusually high melting points, boiling points and things, but also dominates its chemical properties, so it's really important. So partial charges depend, remember, on electronegativity differences, and oxygen is the second most electronegative element, so it's nearly always going to be delta negative. The only time it isn't would be if it was bonded to the most electronegative element, which is fluorine. So we know in this case that that's going to be delta negative, and both the hydrogen and the carbon that it's bonded to are going to be delta positive. So then it asks us to explain why ethanol is a polar molecule. So that's part of the answer. Okay, so we need to explain that oxygen is more electronegative. And electronegative, remember, has a very specific meaning. It means how good an atom of an element is at attracting the bonding electrons in a covalent bond. And oxygen is better at doing that than either hydrogen or carbon. So oxygen is more electronegative than carbon or hydrogen. So oxygen becomes delta negative. But remember, that's not the only issue when it comes to whether molecules are polar. So you might remember the example of, for example, CCl4, which looks like this, if you draw the shape out. And that has polar bonds as well, because chlorine is more positive than carbon. So you get these delta negative chlorines and the delta positive carbon. But that molecule is not polar, because even though the bonds are polar, the symmetry causes the dipoles to cancel. So when you're explaining why a molecule is polar, you've got to talk about the symmetry as well. And ethanol's not a symmetrical molecule. You can see that there is not that regularity of structure that you had in CCl4, so it's not symmetrical, which means that the dipoles don't cancel. And that means that it's a polar molecule. Okay, so make sure you get the whole story there. If you're asked why a molecule is polar, don't just talk about the individual polar bonds, which is the electronegativity bit, talk about the symmetry as well. So then in part D, it wants us to comment on this huge difference really in the boiling points of ethanol and propane. So you can see that at first sight the molecules look kind of similar. I mean, this end of the molecule is exactly the same in both, and you've got a similar size at this end, and indeed if you add up the electrons, you've got 8 plus 1 is 9 in an OH group, and 6 plus 3 is 9 in a CH3 group. So those molecules have the same number of electrons, which would mean in terms of induced dipole-dipole forces you would expect them to be comparable, and yet there's this huge difference in boiling point. And the answer, of course, as to why there's such a big difference is that this can form hydrogen bonds, as well as induced dipole-dipole forces, but this one can't. Okay, can only form induced dipole-dipole forces. So the reason we know that, remember, is that hydrogen bonds are possible whenever you have either OH covalent bonds or NH covalent bonds or FH covalent bonds. In those three cases, this highly electronegative element pulls the electron strongly enough away from the hydrogen to make these hydrogen bonds possible, and only in those cases. So you have to remember that checklist of what the possible bonds are that you have to look for in a molecule if you want to know if it can form hydrogen bonds. And the answer is yes for ethanol, because you've got the OH bond there, but no for propane. That's not enough though. You can't just say that, because they'll say, yeah, okay, why should I care? So you have to then explain why this matters. So you have to say that hydrogen bonds are stronger than induced dipole-dipole forces. And that's getting there as an explanation, but it still doesn't fully answer it, because they'll say, okay, so it's got stronger bonds between the molecules, what's that got to do with it? But the point is, of course, that those intermolecular forces, the hydrogen bonds, the induced dipole-dipole forces, those are the things that have to break when it boils. So if these ones are stronger, that's a harder thing to do. So you need to spell that out, and you need to do it in terms of energy. So you need to say, so it takes more energy. And then to stress that we're breaking them, to break the hydrogen bonds. And that's why ethanol has a higher boiling point. So those melting point, boiling point arguments, you've practiced loads of those now, but you need to keep on practicing them. You need to make absolutely sure that you give the full story, that you don't end up getting 1 out of 3, 2 out of 3, because you say part of it but not all of it. So that's what you need. You very commonly get asked to draw diagrams showing hydrogen bonding between molecules, and the way to approach those questions always is to remember the sort of archetypal one, the one that you learnt first of all, which is 2 water molecules hydrogen bonding to each other. So let's draw that. I know that's not what the question asks for, but we'll use that as our starting point. So there's a water molecule. Remember, the non-linear shape is very important, and the fact that that oxygen has 2 lone pairs as well as the 2 bonded pairs. Now the hydrogen bond results from the fact that that oxygen is delta negative and the hydrogens are delta positive. So you must show the dipoles when you're drawing hydrogen bonds. And it's really just a special case of an attraction between dipoles. So the delta negative end of this molecule is going to be attracted to the delta positive end of another molecule. Okay, so to the delta positive hydrogen there. Okay, so make sure that you've got that right, that it's an attraction between a delta negative and a delta positive. You draw it as a dashed line, not a full line, because it's not a covalent bond, and you make sure it points at the lone pair. They will insist on you doing that when you draw these things. And then you can put the same stuff up here. And that would be your hydrogen bonding diagram for water. Now the question here is, what about two ethanol molecules hydrogen bonding to each other? And the thing to realise is that it's still about OH group in an alcohol molecule hydrogen bonding to OH group in another alcohol molecule. So basically it works the same way, and the only difference is that one of these hydrogens, so let's make it this one and this one, has been replaced with CH2CH3. Okay, so there's your ethanol molecule, and you can see that basically you haven't had to learn a new diagram. It's just the same diagram you've learnt for water adapted, and that makes the next bit very easy as well, because it asks us to say, well, how can our ethanol molecule bond to a water molecule? That's very important, because ethanol is soluble in water, unlike, for example, propane, which isn't. And again, that's because it can form hydrogen bonds not just to another ethanol molecule, but to a water molecule. And again, of course, that diagram's very easy to generate. You just reinstate that as a water molecule, and there's your hydrogen bond between ethanol and water. And so that's a diagram that you may need to draw if you're explaining why ethanol is soluble in water, whereas a lot of organic compounds are not. Question 2 gives us a bit of naming practice on alcohols. So the thing here that you need to sort of know, which is kind of important, is that when you have OH in a compound, in the name that becomes ol as an ending at the end of the name, and that OH group takes priority in terms of numbering. So in other words, when you're deciding which end of the chain to start numbering from, what you focus on is keeping the ol with the smallest number possible, and that gives you the orientation. So in this case, you find the longest chain following the normal recipe. So you've got 1, 2, 3, 4, 5, 6, 7 is the longest continuous chain. So that's hept. It's got no carbon-carbon double bonds, so it's saturated, which means it's an. And it's got the OH group, so it's ol. And I've left the space there for the number. And as I say, you just work on the basis that because that's the ending, you want to keep its number as small as possible. So that means you're going to start numbering from this end. 1, 2, 3, 4, 5, 6, 7. Because that keeps the ol number as small as possible, so heptan 2-ol. And then the only other thing you've got, obviously, are these two 1-carbon branches. So 1 carbon branch, remember, is called a methyl group, and because we've got 2 of them, it's dimethyl. So dimethyl heptan 2-ol. But that obviously is not enough, because those 2 methyl groups could be anywhere. We need numbers to show where the methyl groups are, and they're both attached to carbon 5, so it's 5,5 dimethyl heptan 2-ol. This one is a much simpler molecule, but you just follow the same thing. So your longest continuous chain this time is 3, so it's prop. Again, saturated, no carbon-carbon double bonds, so it's propan. And to keep the ol number as small as possible, the ending number as small as possible, we're going to number the carbons like this. So it's propan 1-ol. And then the extra bit sticking off from the chain is just a methyl group there. So it's 2-methyl, meaning a 1-carbon branch attached to carbon 2. So 2-methyl propan 1-ol. Now this one's obviously a much more complicated looking thing. The root of the name is going to be based on this 5-membered ring here, because you can see that's got 3 different things attached to it: bromine, an alcohol group, and this propyl group, a 3-carbon chain. So the only simple way to name it is to make the 5-carbon ring the root of the name. So remember, a ring gets you the cyclo bit in the name, and because there's 5 of them, it's cyclopent. And because it's saturated, no carbon-carbon double bonds in the ring, it's cyclopentan. Right, so that's going to be the root of it. Now, we've got to get the numbering right within the ring, and again, we stick with this principle that we want to get the number of the OH, the number of the ending, as small as possible. So we're going to call that carbon 1. So cyclopentan 1-ol, with the OH attached to carbon 1. And then we want to keep the numbers for the other 2 groups as small as possible, so we go that way around the ring, not this way. So that will be 2 and that will be 3. So we've got a bromine attached to carbon 3, so that will be 3-bromo. And we've got a 3-carbon branch, which is called a propyl group, attached to carbon 2. So it's 3-bromo, 2-propyl, cyclopentan 1-ol. If you put the propyl and the bromo the other way round, that would be fine. But you've got to get the numbering that way round to keep the ending as small as possible. Now this one is slightly different because it's got not just 1 alcohol group but 2 OH groups. And you've come across the same kind of thing before when we had 2 alkene groups. In an alkene we called it a diene. Di meaning 2 of something. When we had 2 chlorines in a molecule, we called it a dichloro. So, as you would hopefully therefore expect, this is a diol. So again, we want to keep the numbers as small as possible. So we've got 1 at the end of the chain, so let's call this one carbon 1, 2, 3, 4, 5, 6. Okay, so a 6-carbon chain is the root of the name, so that's hex. Saturated chain, so it's an. And then we've got 1 and 5, both have OH groups, so it's hexan 1,5-diol. Okay, so diol means 2 OH groups, 1 attached to carbon 1, 1 attached to carbon 5, hexan 1,5-diol. The only other thing it has is the 2-carbon branch attached to carbon 3, so it's 3-ethyl, hexan 1,5-diol. In question 3, we're going the other way round. We're given the names and we have to draw the structures. Now it just says draw structures, it doesn't specify the format, it doesn't say they have to be displayed or skeletal or whatever, but I would always suggest, given the choice, skeletal is the way to go because it's quickest, clearest, most straightforward. So 3-methyl-pentan-3-ol, so go with the root bit first, the bit that comes at the end. Pentan means you have a chain of 5 with no double bonds in it. Pent is 5 carbons, and means it's saturated. And 3-ol means the 3rd carbon along has the OH group on board. So that's pentan 3-ol. And then 3-methyl means that same carbon, carbon 3, also has a methyl group attached. So that's there. Okay, so that's 3-methyl-pentan-3-ol. Okay, so now 2,2-dipropyl cyclopropan 1-ol. Again, start with the root bit at the end. So cyclopropan means a ring of 3 this time. Cyclo means a ring. And 1-ol means that you have an OH group attached to carbon 1. And then carbon 2, which will be either this one or this one, it doesn't matter which one, has 2 propyl groups attached. Not cyclopropyl this time, just propyl. So these are just chains of 3. 1, 2, 3. 1, 2, 3. Like that. And finally, tribromomethanol. So methanol means you just have 1 carbon and then the OH. So that would be the slightly strange looking skeletal formula for just methanol. But tribromomethanol means that we have 3 bromines on board instead of the 3 hydrogens that you'd have in a CH3 group. So we just have Br, Br, and Br, like that, and that's tribromomethanol.